Hello. So far we've been looking at situations where the objective function that our agent is maximizing is bounded. And that's really useful because it means that we know we're going to have a solution because our problem can't go off to infinity, therefore any infinite sequence has to be contained. However, in many economic applications, this boundedness condition is not going to work. For example, we'll often be working with utility functions that go off potentially to infinity, or with production functions that in principle could go off to infinity. So how do we do dynamic programming in those contexts? It turns out that there are two assumptions that we're going to need that are going to be very natural assumptions to make in the context of many macroeconomic problems. One will have to do with the concavity of utility and production functions. If something is concave, of course, it's not worth putting too much into it past a certain point. The other assumption that's going to be useful is going to be the idea that investment is costly. So, in principle, it is possible to put more and more into production in the future, which of course will lead to increased utility in the future. However, you can only do so at an increasing cost today. And those two things are going to be what helps to keep our problem contained, even when the objective function and production functions are potentially infinite. Let's take a look. All right, here we are back looking at equations, and here in front of us is once again a simple version of the standard growth model. Now, you may remember that we've discussed before how the contraction mapping theorem would apply to this equation, which we call the Bellman equation, to prove uniqueness and existence of the value function. And a key assumption was that the space of functions that we are working with here was bounded functions. Now, here's a problem. In general, as I think I mentioned earlier, the utility function that we're going to use here is not bounded very often. The particular utility function that we're going to use is this. Which converges to log as this parameter sigma converges to 1. Natural log, that is. Second, this production function here may not be bounded either. A very common example of the production function that we're going to use here is this. Again, this is unbounded as well. So the question is, how can we apply these techniques, dynamic programming, the Bellman equation, and so on, in a context where returns are not bounded? So that's what we're going to do now. What we're going to find is that in order to do this, first we need certain assumptions, so that even though these functions are unbounded, there is something about them that's going to constrain them. That's generally going to be concavity. And what this is going to give us is that when we solve this, we're going to have two conditions for optimality that will look, in one case, similar to what we had before. Basically, if we just blaze ahead and take first order conditions and the envelope condition for this, we're going to end up by putting them together with an Euler equation, just like before. In fact, it'll be the same one. But second, we will need two boundary conditions. One of them has to do with what happens at the beginning. And of course, that's an easy one. The boundary condition at the beginning for this problem is that K0 is given. And there will be a terminal boundary condition for what happens at the end of time. But there is no end of time in this problem, is there? The end of time in this problem is infinity. If you remember, the way we got this was from a sequential problem where there was an infinite sum of utility from consumption that this agent was maximizing. The terminal condition is going to be something called the transversality condition. So that's where we are headed. Now, the transversality condition is important because we need to know that it's there, because we need to know that what we're talking about makes sense. In much of what we do, it's not going to come up explicitly when we're looking at applications, but the ultimate application of any model in macro, especially if it's in the business cycle literature, is going to be a simulation of your model economy. It turns out the transversality condition, or at least some broad intuition stemming from it, is going to be key to being able to simulate these economies. If we have time, we'll talk about that eventually as well. All right, so the first thing I want to do is to try and write down a more general version of this problem. What we're going to do is we're going to write down the initial sequential problem that we had before, but let's just make it more general. So instead of saying it was v of k, this is v of some x, which is going to be some state variable. Whether it's capital or something else, doesn't matter. And we're maximizing an infinite sum. Here's a general formulation of a problem of this kind. The infinite sum of some discounted function that depends both on the variable at this state and the variable at the next state. So, and of course, we're maximizing the entire sequence. I guess to be careful, we're not choosing xt because t0 is given, we're choosing t plus 1. You can see how this is a generalization of this. If we say that capital is x, then u is going to be the utility function here with this replaced instead. I guess I can do that. Remember, this was u of ct. Now I can replace this in here. And lo and behold, this would then become my big U of xt and xt plus 1, where xt is, of course, capital in this case. And this is going to be subject to xt being drawn from some set gamma, xt plus 1 should be drawn from some set gamma that depends on xt. And of course, x0 is given. Now is where we need some assumptions to make this work. So the first assumption is going to be that x is an element of the positive reals, and note that it's to the power L. In other words, this could be a vector. You could have multiple variables that the agent is taking as given on date 0 and then choosing that will then constrain them in the following date. By the way, any such variable which you start by taking as given, but which you're choosing for a future date, which will then be something that you take as given then, we refer to as a state variable. So the state variable is positive and could be multidimensional. The second assumption requires us to define a new object. Define the following: the graph of gamma. Remember, gamma is this set from which you must choose your future x, and it could depend on your current x. So the set from which you can choose your future capital depends on your current capital through this production function. The graph of that is the set of pairs x and y such that x is an element of x and y is an element of gamma of x. The assumption is that the graph of gamma, self-convex. You should know what convex means. If it has, for any two elements in the set, in this case the graph of gamma, any points in between those 2 points must also be in gamma. Also, the zero vector, where 0 is of the correct dimension here, should also be in the graph of gamma. Next, notice that u is a function that maps from the graph of gamma into real numbers. U must be continuous differentiable and concave. Here is concavity. Next, we need that for any pair xy in the graph of gamma, we need that the derivative of u with respect to y is less than or equal to 0. Now, what does this mean? Remember, x is the first element and y is xt plus 1. So if x is capital today, then y is capital tomorrow. So the derivative of u with respect to y is the derivative of u with respect to your investment in future capital. That must be negative or 0. In other words, investing in the future is costly now. This is a clearly important assumption that has a very clear economic interpretation as well. Finally, for any feasible, that means allowable path xt defined at all dates, we have that the limit, following limit exists. And the limit that we're interested in is the limit as t goes to infinity, that's big T, of what? The sum from 0 up to that T of the discounted function here. We need that limit to exist. What does this mean? It means that for any feasible function, any feasible sequence of investment, you can never get infinite utility in the long run. That's going to be related to this, of course, right? Not only is it costly for you to invest in the future, but it's sufficiently costly that in some sense, there's no feasible path that would allow your utility to explode. Any feasible path has to yield finite utility, finite discounted utility, even in the long run. Finally, here is the climax of this video. We're going to define an optimal path in an intuitive way, which is very simply that if an optimal path is defined as some sequence xt star, an optimal path naturally is very simply that the discounted utility from the optimal path must be greater than or equal to the discounted utility from any other path, where xt here could be any other feasible path. Then there is a theorem which is due to Kamihigashi that under our assumptions for any interior optimal path, and of course interiority is key here since we are in an unbounded region, the following must hold. In other words, this is a necessary condition. The limit as t goes to infinity of the discounted marginal utility, so that's the derivative of u with respect to the future investments, the second argument, evaluated, of course, along that optimal path, times the future investment itself must equal 0. That is a necessary condition for an optimum in this context. Now, some authors have an alternative formulation of this condition, which is that the first derivative times xt equals 0. And you can readily demonstrate that these two are the same because this one is the same as this one combined with the Euler equation. So we are just going to state the result here. And in the next video, we will prove this result. So that's the result. In the next video, what we're going to do is to have a little look at the proof for whether transversality condition is necessary in this context. And again, this isn't something that we'll need to necessarily worry about day to day. Often the Euler equation will tell us what we need to know. But in a business cycle context, the transversality condition is going to be key for us to be able to simulate these models. See you later.